We're now going to look at graphing a logarithmic function. And before we get into that, I want to look at how we can find the inverse function of f of x equals 10 to the x. Because here we're looking at your exponential function, and in order to find the inverse function, we're going to have to use our logarithms, and then we're going to look at graphing the logarithmic function that we come up with. So recall, if we're looking for the inverse function, we have to think of this as y equals 10 to the x, because f of x is really our y. And remember, we switched the x and y values, so we're going to replace y with x, and we're going to replace x with y. And now, once we switch our x and y values, we're going to solve the equation for y. Well, the problem is y is up here as our exponent, so we need to get rid of that. And the way we're going to do that is we're going to take the log of both sides. So for an example, if we have x equals 10 to the y, then our base here is 10. And if you think back to our properties, remember we said when the bases match up, they will cancel out. So if I take the log of this, and specifically if I take, and I'm going to write the base in, it's understood to be a 10, but I'm going to write this as log base 10 of 10. Remember, that's going to cancel out and leave us with the exponent. But if I take the log here of the right-hand side, I've got to do that on the left side as well. So that's log base 10 of x. Okay, so now what's going to happen, we're going to be left with log base 10 of x equals, and again, this cancels out, so we're just left with y. And remember, this is going back to those properties where when these match up, they're going to cancel each other out, and you're left with the exponent. So now we have actually found the inverse function. So this y, or the f inverse of x, is equal to log base 10 of x, or simply log of x. So keep in mind, we don't write a number down here. This is understood to be base 10. So here we had the function 10 to the x. This is your exponential function. And the inverse function of that is log base 10 of x. So you'll notice here that these are inverse functions. So I want to look at the graph of f of x equals 10 to the x. And we can go to the calculator and do that. We can say y equals, and take 10 raised to the power of x. And of course, if we go to zoom standard, we can see over here we have our graph that we're familiar with. But now I want to go back and look at the graph of the function that we just found, the inverse function, which is the logarithmic function, log of x. Okay, so if I go down to y2, we can type in log x. And notice the graph here is here at the bottom. Okay, and remember, what's the relationship of a function and its inverse? Well, if we go back here, what if I graph the equation y equals x? Then remember, that gives us the diagonal line. And I'm going to, let's see if I zoom in a little bit, if that helps. Zoom to, I think that'll look a little bit better for us. So if I take and copy this into our notes here, notice what's happening here with the graph. And this is where I want to emphasize that we know that this here is the line y equals x, this diagonal line. And the graph up here at the top, this is our function f of x. And what we found down here is the inverse function. And remember that a function that's inverse is a reflection in the line y equals x. And that's what we have here. If you fold this, if you were able to fold this screen on this diagonal line, function f would fall right on top of the inverse function here. Now, I want to go back and review a little bit with the original function here, f of x equals 10 to the x. So if we're looking at this graph here on top, let's review what's happening with this graph. First of all, what is the domain? Well, the domain, realize your x for this function f would simply be all real numbers. What is the range? Well, it never goes below the x-axis, so the range is y is greater than 0. And we do have a horizontal asymptote at y equals 0. Okay, that would be here. And we also have a y-intercept at 0, 1. So here's your y-intercept. Okay, so that's all the stuff we've talked about here with the exponential form. But now when we find the inverse, we have a logarithmic equation. And down here, if we want to look at this logarithm, let's look at the graph and see if we can determine what's the domain here. Well, clearly here the domain is going to be what? Anything that is greater than 0, because notice here the graph never crosses the y-axis over here. So your domain is going to be x is simply greater than 0. And of course your range, because this goes down and up forever, would simply be all real numbers. And this time, instead of a horizontal, we're going to have a vertical asymptote, okay? And that's going to be right here at the y-axis going up and down. So that would be x equals 0. And here, instead of a y-intercept, we're going to have an x-intercept at 1, 0. Now, what you might want to do is actually take and recall the relationship for your function and its inverse is to compare this information. Notice here your range and domain are switched, and if we compare here the domain and the range, okay, and then of course here we have a horizontal asymptote where here we have a vertical. And if we notice here, we have a y-intercept at 0, 1, and here we have an x-intercept at 1, 0. And again, that's because these are inverse functions. Now again, the main thing we want to look at though here is graphing this logarithmic function. So what I want you to realize is the graph of this log function is going to have this base graph like this here going through the x-axis at 1 and having a vertical asymptote here at x equals 0. Okay, and that's going to be the basic shape for any logarithmic function. The only thing that's going to change is maybe how fast this graph is going to increase. For an example, if we go back to the calculator and if I type in our log of x and then here for y2 I'm going to type in the natural log of x. Now keep in mind this is really no different than the log of x except for the natural log, instead of having a base of 10, the natural log has a base of e. So let's look at the difference. So the first graph we're going to see here is our logarithm, okay? And then the next graph that's going to show up here is our natural log, okay? So really the only difference between these graphs is how fast they increase, okay? So realize they are going to still have the same basic shape. So here if I go to zoom standard, we can see this a little bit better. So there's our log base 10 and here's the log base e, which is the natural log. So if you notice, it's just going here a little bit faster on the y-axis than the logarithm. So you're still going to have the same basic shape. And that's going to be true for any logarithmic function. So let's look at another example here. Let's say that we have log of x minus 2. Now, if we think about all of those transformation properties we had before, let's see if we can guess what this graph is going to look like. Well, we already know the basic graph of our log function. We know that it's going to cross at 1 on the x-axis. We know the basic graph is going to go something like this, right? And we're going to have here at the y-axis we would have a vertical asymptote, okay? Now, what is the x minus 2? Well, notice this x minus 2, just like we talked about before, this is on the inside of the function. So that's going to affect our graph to the left and to the right. And if we were to take this x minus 2 and set it equal to 0, we would get x equals 2, which means our graph is going to move 2 units to the right. So if we start from here on the x-axis at 1, if we go 2 units to the right, we're now going to be at 3. So this is now where the graph is going to cross the x-axis. Now, what happens to the vertical asymptote? Well, it's also going to move 2 units to the right, so the vertical asymptote is now going to be at x equals 2. So this is the new vertical asymptote. So your graph is going to look basically like this. It's going to be the same shape, it's just going to move over 3 units to the right. So if we look at this closely, then we know we can find the domain. And again, the domain is basically found by what's inside the parentheses. Because remember, we cannot take the log of anything that is 0 or less. So we can only take the log of values that are greater than 0. So for example, if we went to the calculator, and if I was to type in log of 0, notice we get domain error. Okay, and that's because we cannot take the log of 0. Notice we can take the log of anything greater than 0. So if I was to type in, let's say, the log of 0.25, we get an answer. Or if we were to type in the log of 1, okay, which is 0, we know that from before. And if we type in the log of 2, so realize when we take the log of something, that has to be greater than 0. So really, the easiest way to find your domain of a logarithmic function is to take the x minus 2, which you're taking the log of, and set that greater than 0. So if we solve for x, that tells us that x must be greater than 2. And from the transformation over here on the right, we can tell that we have a vertical asymptote. And we know that the vertical asymptote is going to be x equals 2 because that is what makes this part here equal to 0. And if that goes to 0, we cannot take the log of it. So that's where the vertical asymptote is going to occur, where this quantity is equal to 0. All right, what else do we need to find? That's the domain, the vertical asymptote. What is going to be the range? Well, has our range changed? Well, the range is still going to be all real numbers because this graph continues down forever and it continues slightly going up, so the range would be all real numbers. And we already said our x-intercept here. We have the x-intercept. That's going to move over 2 units, so instead of at 1, 0, it's now going to be at 3, 0. Okay? So realize that all of the things we've learned in the past for graphing our functions, and as far as the transformations, those are still going to be true for our logarithmic functions as well. All right, and I want to look at one more example to point out the fact that here we have a natural log, and for some reason everybody thinks this is different, but realize this function here is really no different than saying f of x equals 5 times, if I was to write it out, log base e of x plus 3. So this is still a logarithmic function, it's just that this ln means that our base is simply e. Okay? So we want to figure out what's going to happen here to our logarithmic function. Well, we already said before the natural log is still going to have the same basic shape. It's going to look a little bit different because of the base is e instead of 10, but we know that the basic ln function is still going to cross here at 1, and it's going to look something similar to this here. So this is our just basic natural log of x function. So what effect is the 5 having? Well, the 5 is going to actually make it go up a little faster, so this curve is going to increase more. But what effect is the x plus 3 going to have? Well, once again, if we take the x plus 3 and we set that equal to 0, then we get x equals a negative 3. So that tells us that our graph is going to move 3 units to the left. Now, this is where you got to be careful. this graph doesn't start at the origin, it starts at 1. So if we go 3 units to the left, we would count 1, 2, 3. So 3 units to the left is actually going to put us here at a -2. So you got to be careful here. So if we're looking for the domain, once again, that's where we would take this x plus 3 and we would say that has to be greater than 0. So that means x has to be greater than -3. Okay. Now, x has to be greater than -3. Well, if we notice, if we put a -3 here, that's going to be our vertical asymptote at -3. So the domain has to be greater than -3, but the vertical asymptote then will occur at -3. So that means the graph is going to look something like this here. And then, of course, the range, once again, would simply be all real numbers. And then our x-intercept, which we've identified already, because we're moving 3 units to the left, our x-intercept would be at -2, 0. Okay, so that's basically it for graphing our logarithmic functions. And I do want to point out what would happen if I changed this example up here and I said plus, let's say, 4. Well, notice the 4, if I kept 5 ln of x plus 3 and put a plus 4 here, this 4 is on the outside, so all that's going to do is move this entire function up 4 units. So then your graph would look more like this, because this graph then would be moved up 4 units, just like we said before. Anything on the inside is going to affect here the x plus 3. Anything on the inside is going to move the graph left or right. Anything we add or subtract on the outside is going to move the graph up or down.